Thank you for joining me today in part 2 of the longest palindromic subsequence, not to be confused with substring. In part 1, I briefly went over what the problem was, so if you haven't watched that first, be sure to click the gray tab in the upper right corner that's appearing now, and then come back. In this video, we will examine the code, and we're going to go over it step by step. We will use the word banana, also used in video 1. Remember, there are a few palindromes within the word banana, such as ANA and NAN, but we want the longest one, which is ANANA. Remember, palindromes are words containing letters that are the same when reversed. They encircle a single letter in the middle, and the letters are the same on either side. Remember the diagram I showed in part 1? I redid it here using our word banana. As you can see, when you do your counting, we get to the upper right side and you can see visually that 5 is the number of the longest subsequence in the string for the word banana. If you look here, you can see the maximum number for ANA and NAN is 3. Alright, let's start coding. This example here was my first attempt, and I'm showing you for learning purposes as it is a prime example of what not to do. Feel free to pause it and have a few chuckles. Hey, remember the candy chuckles? Man, I love those. Anyway, I thought I was being super brilliant using a numpy zero matrix to store the information. Wrong. Once I took that out, thereby eliminating the for loop, I was finally able to pass the test and not time out. The second example here gave me success, but it just wasn't fast enough, at least in my opinion. So I tweaked it a bit and took out the len variable of n and just replaced it with the actual len of s. This sped it up the most, and I got the fastest time of 2380. And before we look at our last example, let's go over this code as it is a fairly common solution floating around. To me, it's the easiest to read. So let's look under the hood and examine the moving parts. Our variable m creates 6 lists of zeros, or a 6x6 table. This is the place we will store our information. Remember, again, in dynamic programming, we are storing information for easy recall to avoid redundant calls or inputs. You can do this by creating tables, lists, dictionaries, or matrices, but keep in mind that creating additional iterations with for loops creates expense. For this code, we create 2 for loops. You could look at it like creating 2 strings and slicing off the head of one string and the tail of the other, like this. And the mechanics of it work in this way. Hey there! If you made it this far and enjoy what you're seeing, why not subscribe? I upload fresh content all the time. Thanks for watching. It looks at I0 and goes through J1, 2, 3, 4, and 5. See the pink section to the right? Once it goes through that loop, it moves into I1, the tan section, and I1 goes over J, 2, 3, 4, and 5. It doesn't go back in J, it keeps moving forward till the end. Then it moves to I2, the light green section, and so on and so forth. Feel free to pause any of the slides for further study. And what it's doing during these iterations is storing up the information according to the parameters we have set in our if, elif, and else statements. Since I is already established, we need to create a variable for j and make it I plus the substring of our first loop. I named it SS in the first loop, as you can see here. Basically, as we store our information into our table of zeros, we are looking for 2 things: a match of letters or no match of letters. That's really it. Do we have a match or not? And what do we do in either instance? If we have a match, it must meet one of 2 criteria: that it matches and is at least a substring of 1. When that happens, we need to change it to 2. Then, when we have a match, our I and j square has a 2 added to it. If we don't have a match, it stays a 1. And as we move through our loops, it's either adding up or taking the max from the previous I and j square, whichever one is greater. And then, at the end of it all, when it's done looping through, we are returning the last upper right square of the table. Simple enough, right? Kidding. It's actually pretty hard, but we have to keep learning, don't we? The last solution comes from user Gingerun, I think I'm saying that right, and he uses the cache from the FuncTools module, and it's absolutely amazing. To learn more about caching, I'm going to put a link below that you should check out sometime. It's pretty useful information and a great tool to put in your belt. Under the longest palindrome subsequence function call, another function is created for I and j. It's so much cleaner and totally more efficient, as the runtime is like a whopping 2/3 faster than my original formula. It's similar in structure, so just feel free to compare the two. Again, it's pretty mind-blowing. Thank you for watching, and I hope this video was helpful to you. Daily videos throughout the week are coming out, so don't forget to subscribe.